So we're ready to start. Of course, everybody knows what a simulation is, but we still will need to go through a number of things and how they affect the accuracy of the simulation output. I said everybody knows what a simulation is, but perhaps it's worth sharing our expectations about what simulations are. So I invite you to use the annotate feature of Zoom and write your own answer to this question on this screen. What are the things we see here? A simulation is a tentative to reproduce a reality, an imitation of an experiment that is supposed to be, a simulation of an approximation of a real system, or generating data that are similar to the real experiment, but without doing the experiment. All of this is absolutely correct. When perhaps everything you said is true, but what differentiates typically a simulation from a real measurement is that in a simulation, we do everything in the computer. We write programs that imitate reality, and everything runs in the computer, which is good and bad, as we will see. It gives us full control on the hidden factors, for example. There are important differences between simulation and real implementation, which are very important for us, for what we do. One is that typically events will be serialized. In the real world, if I'm simulating a web server, for example, that has lots of parallel machines, and there are millions of customers going into this place, many things will happen in parallel. For example, the think time of users happen in parallel. Typically, when we do a simulation, we have to serialize events. Even if we do parallel threads, we typically need to serialize events. For example, we will need to consider that an arrival occurs before the start of service occurs. And so that's one of the things that we will have to do as an implementer. And while serializing events, that gives us an opportunity to manipulate the time. So that's the major difference for the type of simulations that we are discussing. It is that the time is simulated. It's not real time. It's also called discrete event simulations. We will advance the state of our system when an event of interest occurs. We don't need to simulate every nanosecond of time if nothing interesting happens. So the simulated time can move much faster. For example, if nothing happens, if I'm simulating a queuing system and between two arrivals, nothing happens, or two departures, then I don't need to worry about it. So it can be faster. But it can be also much slower, which is more typically the case. We want to zoom on a large number of events that can occur, and we can run them in simulated time by taking all the details into consideration. So the time at which the computer advances the simulation is typically not at all the same as real time for the type of simulations that we do of computer and information systems. There are specific simulations which are called real-time simulations that will reproduce a physical system, for example, an electrical grid, in exactly the same time as the physical system would do. But that is a very specific, very different type of simulations. Doing that is very difficult. You need to make sure you have enough computing resources so that the computation of all your events is fast enough to be able to advance at the same speed that it would be in the physical system. We will not consider these in this course. We will consider simulations where we have the concept of time, but the real time has nothing to do with the simulated time. Another important difference in a simulation or in, I would say, artificial experiments is that we typically have the problem of initialization. If I simulate a if I want to measure what happens on a system, like a road system or a computer system, typically this system is working. So I can come with my instruments, observe things, and see and measure the metrics of interest. When we do a simulation, the system is not working. And as we will see, we need to think about what happens, what is the impact of the initial state. For example, if I'm simulating a web server or a web farm, and I start with everything empty, with no customer in the system, perhaps I'm starting from a non-typical system, and that might distort the output of my simulation, the metrics I'm doing. So this is something we'll need to keep in mind. There is also an important difference in types of simulations that we do. Here I'm giving two simulations. The first one is the time to complete n jobs. So I have, for example, a job completion system, for example, Joe's shop that you're looking at in lab 1. So jobs that are requests for downloading contents arrive. And we want to estimate the time it takes we have a batch of n customers that arrive, and we want to estimate the time it takes to serve all these n customers. So it is a snapshot of an event that occurs, and it has a well-defined beginning and a well-defined end. Simulation 2 is perhaps the same, but here we're interested to estimate the time it takes to serve one arbitrary request. So the system has been working for a long period of time, and we want to see what happens. What is the expected time to serve one request, or what's the distribution of times to serve a request? So simulation 2 has to do with the quality of service perceived by a user. Simulation 1 has to do with how much time I'm able to serve a batch of users, which is the quality of service not by each individual user in the batch, but to do the complete work. So the metrics are different, but from a simulation viewpoint, there is an essential difference, is that the first one is a terminating simulation, whereas the second one is not terminating. Terminating simulation means I run an experiment that has a well-defined beginning and a well-defined end. I measure things during this simulation, and when the experiment is over, I know that it is over. Which seems to be normal, that should be the case, but it is not always the case. In fact, most simulations of computer and information systems are not of that kind. They are more like the second simulation. This simulation does not terminate. We would like to see what happens on a busy web server. And this busy web server, at the time scale where we simulate things, the busy hour is very long. So there will be millions of requests served during a busy hour. So we see it more like something that does not terminate. And the question here, the practical question, is how long should we run it? To illustrate the difference here, here are two graphics that show the output of two runs of the same simulator where I've changed only one parameter. On the x-axis, I'm showing the time in millisecond to the power 4. On the y-axis, I'm showing the queue length average over a small window of time. So it's the mean queue length over a small period of time. Be careful, the y-axis scales are different. On the left, we go from 8 to 28. On the right, we go from 10 to 160. And the time is the same. The only difference between those two systems is that on the left, the average service time is 96 milliseconds for a job, whereas on the right is 101 millisecond. And in both cases, the requests arrive at the same rate. So you can think of scenario 1 and scenario 2 as two different implementations of the software. Scenario 1 was version 3 of Joe's Shop software. Scenario 2 is version 4, where we've upgraded the system. And as you know, when we upgrade the system, most of the time, the practical result is that the service time is increased here. The curves appear to be very different, right? So if we look at those two curves, we see fundamental differences. How would you qualify those differences? So let's try to annotate again. The fundamental difference between the left and the right are that can be viewed from different viewpoints. One way to say that is that the annotation that is given here, the right queue, seems to be unstable. And that's exactly what is happening. If we look at the queue size here, we see that on the left, it starts from a small value. That's the initial value. Remember, when we do a simulation, we have to choose initial conditions, and they are perhaps biasing the system. But we see that after some time, the queue increases and then fluctuates. Here it increases, decreases. Probably if we would continue the simulation long enough, it would continue to fluctuate in a very similar way as it did here. So keyword is stability. And another aspect of stability is that it fluctuates. It's not constant, right? The queue size is not fixed to 24. It is random and will always be random, even if we continue the simulation for a long period of time. But it appears to be drawn from the same distribution in the sense that it appears to be stationary. We don't observe a pattern over time, except for the initialization phase. So another concept is stationarity. Here it is stable, and after an initialization phase, it will have what we can call a stationary regime. In the second case here, we have a queue that is unstable. In fact, it is growing, and it is growing linearly over time. And if we analyze why it's growing, well, it is because the input value is, we have 10 jobs per second, and every job takes a little more than 1/10 of a second. So there is 1% deficit in the processing power. So the queue builds up at a rate of 1% here. So which is what we see here, and that explains, that is why it's linear, because as a first approximation, this system is much more deterministic than this one. Here, the major component is a linear growth plus a random noise around it. And also it is unstable. It continues to grow, which means that if I continue the simulation after a long period of time, I will have very different values on the y-axis. So it is not stationary. And in practice, of course, what will happen is there will be queue overflow. An essential property of a simulation when we do discrete event simulation, when we simulate computer systems, is the concept of stationarity. If we have a simulation that is terminating, we don't need to worry about it. If we simulate how much time it takes to do a certain class of a certain set of jobs, then we start from all the jobs arriving or arriving at a prescribed set of instance, and then we finish. But for simulations that are non-terminating, the issue of stationarity is very important. So what is stationarity? Stationarity is a property of a mathematical model. For example, if we have a stochastic model, so stochastic model means I have a means to produce a simulation that at every time t will produce a value. Xt now is not necessarily a number, it is anything that represents the state of my system. Like you will be doing in lab 2, we will be doing simulations of some systems. So we have a computer program that produces at every time t something that we can measure and observe. And that produces something that we could observe, but also that has a state xt in the memory of the process that is representing the simulation. Then we see that this model is stationary if that is true. For any offset s, the joint distribution of t at time t1, t2, tn is the same as at time t1 plus s, t2 plus s, tn plus s. So that's a very complicated mathematical way of saying, in distribution, if I look at two windows of the process that are shifted by s, there is no statistical way to say which one is which, because they have the same distribution. If I give you a sample of this or a sample of that, if they come from the same distribution, then there is no way to know which one was the earlier one, which one was the first, which one is the second. So in plain English, that means the simulation does not get old. Over time, the behavior of the simulation remains always the same. Again, the simulation will produce random output, like we've shown in the previous diagram of the queuing system on the left. It will continue to oscillate and vary, but the statistical properties of this variation are the same over different windows of time. That's a way of understanding stationarity. I should stop the annotation. So back to a little excursion to the hidden mathematics between stationarity. We will know in practice to know whether the sim was simulating, whether we're doing a terminating simulation or not. If we're doing a non-terminating simulation, we'll have to address the issue. The model that we are simulating, does it have a stationary regime? Is it becoming stationary? To understand this, the theory of Markov chains helps us. So a Markov model, what I described before, a simulating output, which is called in mathematics a stochastic process, is a Markov model if the state continues everything you need to continue the simulation. So anything we simulate in the computer, or quasi anything we simulate in the computer, is a simulation of a Markov model. The only exception would be simulations that take random inputs from the environment. So if you take random inputs from the environments, then perhaps this is not the case. But if we have a simulation that does not interact with the environment, so like we classically do, we want to simulate our next deployment of our web infrastructure, for example, then we simulate its behavior, and then we run the simulation with simulated time. So of course, at every instance t of the simulated time, in order to continue the simulation program, we have to have the state in the simulator. Otherwise, it's not possible. So this is how computer programs work. They work from a given state here. I'm not talking of quantum computers, I'm talking of classical computers here. So anything we simulate in the computer is an instance of a Markov model. Now, in practice, Markov models that are over a discrete state space are very easy to analyze. Discrete state space, that means if the state taken by the simulation is discrete, right? So it can be quantified by integers. Of course, in reality, in the computer, everything we do is discrete because we have a number of bits in the memory, and we cannot do more than 2 to the power of the number of bits that are available. But that's a bit theoretical because in practice, 2 to the power of the gigabytes of memory is an astronomically large number. So in practice, when we do simulation in the computer, we're not necessarily over a discrete state space. However, this discrete state space allows us to understand what happens easily. If you have a Markov model, there's only a certain number of things that can happen. If you run the simulation long enough, it will either walk to infinity. That means it will cause, in practice in your computer, an overflow somewhere. It will try to compute something and does not have enough memory to compute it. Or it will converge to a stationary regime. Those are the only 2 behaviors here. For example, we've seen the 2 examples before. If we have a queue where the utilization factor, utilization is the ratio, is the long-term average of how much of the resource we used. For example, we had a queue that had 10 arrivals per second. If the job was taking 90 milliseconds, and it's a single processor, single core system, then the utilization is 90 milliseconds divided by 100 milliseconds. That gives 90%. If the utilization factor is less than 1, then a queuing system is typically stationary after a transient regime. If it's larger than 1, it is unstable. So the 2 examples we've seen are really prototypes of what we will see quasi always with Markov model here. More specifically, if we have a discrete state space and if it is finite, if it is fully connected, that means every state can be reached from any state. That means if I start the simulation in one state, and if I pick another arbitrary state in my space, there is a path that is possible to go from one state to any other state. How long it will take to this path might be astronomically large, but if there exists a path, then such a simulation typically has 0 or 1 stationary regime. 0 corresponding to the case where it is unstable, and 1 stationary regime, which means that the stationary regime is unique. If it is not strongly connected, that means there are transitions that are irreversible. Once something happens, you cannot come back. For example, you might have a model where you model the death of some components and you don't model the repair. If you assume that in your model some components can die, can be broken, and are never repaired, then once something is broken, you cannot come back to a state where it was not broken. So this hypothesis is violated. For systems like this, there may be several distinct stationary regimes. For example, if you had systems that can have a certain number of failures, they might be in stationary regimes with 1 failed components or 2 failed components or n failed components. So they might move to different stationary regimes. Why am I saying that? Well, this is because it's important to reason qualitatively about what happens to the things we are modeling. In particular, we will always need to know whether a model that we're simulating, when I say a model, that means a computer program that's producing an experiment in the computer, whether it has a stationary regime or not. Now, knowing that in general is an extremely hard problem. In general, if I give you an arbitrary computer program that produces a simulator, and I ask you, does it have a stationary regime? Then it might be a very, very difficult problem. And even for queuing systems, there are still open issues of when some things are stationary or not. However, there are important models where we think that we have at least theoretical reasons to believe it is stable. For example, for many queuing systems, we have positive results and negative results. For example, the single server queue, as we will see, it is always stable and has a unique stationary regime, and there are mild assumptions if the utilization factor is less than 1. If it's larger than 1, it will not be stable. If it is equal to 1, well, that's part of those academic interesting research problems where it's hard to know what really happens. In practice, so there is one aspect, and we will see in this course 2 categories of models. We will see a category, we will see queuing systems, so we'll talk a bit about queuing system in order to help us understand whether the things we are simulating has a hope or we could reasonably expect that it has a stationary regime. We will also see a class of simulation models, and we will discuss that in the pound calculus framework. Time series models, also when we will discuss the forecasting, those are systems where we know very well whether there will be a stationary regime or not. There are other aspects to look at. In particular, reasoning about your system may give you indications. Of course, the real system is always different from what we are simulating. For example, if I'm simulating the performance of the backend of of a data center, of course, I will not simulate every aspect of what happens to the backend. The backend might be subject to a lot of work when there is when the mission that the data center is providing is heavily loaded, for example, during the day, if it's used in a certain time zone, or when it is used for certain computing experiments. There will be other periods, the off-peak period, where it's much less busy. Do I want to simulate all this or not? Well, that's part of the definition of the performance evaluation study that you're doing. Sometimes we want to study what happens during the busy period. So we will hypothetically assume a stationary system that is a reflection of what happens during a busy period. So we take a snapshot of 15 minutes during a busy period, and at the time scale of the data center, there are lots of nanoseconds inside 15 minutes. Therefore, we will take a model that is stationary here. This real system is not stationary. Of course, a computer system will age, it will become old, but we model it when we model the peak hour, for example, as something stationary. In other cases, we are not interested in having a stationary model. For example, if we expect our system to have growth, and the question we're asking is not what is the tail distribution of delays during the most busy hour of the year, but it is another question like, when will my system overflow? When do I need to buy new equipment to upgrade it? So if I'm modeling the growth and perhaps the seasonality, I will use different models and I will think differently. If your system has growth and seasonality, it will not be stationary. So it's important to know which system you're talking about. Are you talking about a system that has a stationary phase or not? Once you believe your model is stationary, we have seen that there is always the impact of initialization. So this theory of Markov chains says that whatever the initialization, if the Markov chain is a good one, an ergodic one, that's a synonym for a good one. Good one means one that has a stationary regime, a unique stationary regime. Then whatever the initial condition, it will move to the stationary regime in a time that can be approximated by an exponential duration. But the rate of the exponential is very hard to compute. It has to do with what is called the mixing time of Markov chains. In practice, when we simulate a real system, we cannot analyze the mixing time exactly. We analyze the mixing time for very simple models that are worth spending a lot of effort on. So what we do instead is eliminate the impact of initial conditions by looking at some typical output. For example, in the case that was here, I can start measuring over a window of time the average queue size, and after some time I will see that it doesn't vary a lot. Here graphically, perhaps at this time here, 10 to the 4 milliseconds, so after 10 seconds, this system appears to not be moving too much. So that's the idea. Of course, we can make this more systematic by taking algorithms to know exactly when the stationary regime starts, but it is not more intelligent than that. The only thing we do is try to see metrics that will stop moving. And typically, if the thing is stationary, then taking an average of the state should not move too much. It's also important to understand reasons for non-stationarity. I've mentioned two easy ones. If it depends on time, if your system is growing or has a periodic behavior, it's different at night or in the day, of course, it will not be stationary. It will not be stationary because I can see on the output of my simulation whether it's day or night. So the definition of stationarity, remember, is that we cannot see where the old and the young part is. We have seen for queuing systems, or in general for systems that have resources, whenever the resource utilization is larger than one, then there will be a problem, so they will not be stable. When the resource utilization is less than one, perhaps they're stable, but they're not all stable. There might be things like deadlocks that prevent resources to be used entirely. So that is domain specific. So this is well known and fairly easy to predict. You will see whether your system is exploding or not. There is something more subtle that we will discuss in detail in a few more lectures. It is what we call a freezing simulation, where the symptom in a queue that is unstable is that the queue explodes, it becomes hot. But there are other non-stationary behaviors, that is when the system becomes cold, a system that freezes over age. We will see that that happens in some cases, for example, but one of the reasons for this to happen when there are rare events that have a large impact. So if a simulation, we will see, for example, in mobility models, if we simulate an event that takes an extremely long time to complete, but it takes an extremely long time to see such an event because it is rare. So if I do a short simulation, I will not see such an event. So the simulation will run and will do its job very fast. But if I do a bit longer simulation, I will see one of these huge jobs that are coming and that block everything for a period of time. And if I wait longer, I will be more likely to see bigger and bigger jobs that come that will take more and more time. So if I do a very long simulation, I will see things that I will very probably, not certainly, but very probably will not see on a short simulation, right? This is similar to what happens when we observe, for example, floods, the level of a river. If you observe the river or temperatures, with the climate change, that's very similar. If you observe the temperature over a short period of time, you're not likely to see the very rare excursions. But if you see them, if you observe over a long period of time, you're more likely to see some of them. So that is an embarrassing thing. If that happens, your simulation is not stationary. So that might be an issue. And we'll come back in detail on how to detect this and how to go about it when this happens. Voilà, time for a little quiz. Here I'm doing perhaps the simplest of all simulations. I have a distribution F. F is the CDF, for example, a Gaussian normal distribution. I have a computer program that allows me to draw a number from F, and my simulation simply consists in drawing repeatedly and independently a number from the distribution F. For example, here's a sample from the Gaussian distribution with mean 23 and variance 100. Does this give a stationary simulation? What is your opinion? I close the poll in a few seconds. Closing. The majority says yes, which is the correct answer, because the joint distribution of a finite number of samples remains the same if we shift the time, because they are drawn from the same machinery here. So it will be independent to see whether a simulation is young or old. In fact, what I'm doing here, I'm showing a much, much larger simulation. And this is illustrating what similarity stationarity really means. Of course, if you look over a very short period of time, you might see periods where the value is decreasing, other periods where it's increasing, but this is random. There is no reason why this happens at this time or at another one here. So there is no signature of time here. That is the simplest example of a stationary simulation, but that already contains a lot of the mental model you should have of a stationary simulation. It is that it continues to be variable, but its variability does not change. Voilà, so we've spoken of simulation, random simulation. Of course, we could do deterministic simulation, but that's very rare in our context. We do deterministic simulation. That means a simulation that computes only one output. But typically, if we want to simulate things, we want to simulate the behavior of something that will be deployed in the field. So we will need to simulate the behavior of user, and that the simplest way to do it is to have stochastic probabilistic model for the things that are unknown. For example, if you want to simulate a charging station for electric vehicles, if you simulate a benchmark that is completely deterministic, you will have very limited information about the performance of your system. So most of the time, we have a stochastic simulation. If we have a stochastic simulation, that means the output is random. We will see how we do a stochastic simulation in a few more minutes or next week. We will, of course, need to have some source of randomness and a program that simulates the logic that embodies the logic of the system that we're interested in. Here is, for example, 30 runs of Joe's shop time to serve a batch of n customers. So here there's no problem of stationarity. It's a terminating simulation. However, there is still some randomness. I've simulated how the customers arrive and how the server works and what documents they're asking for. So there's a bit of randomness. And I see that if I have 10 customers, here is a total service time for 10 experiments or a small number of experiments, 20 customers, 30 customers, 40 customers. So that's very typical of what we have. That's very simple here. In practice, it will be a bit more complicated, but this is very typically what we have. Now I could ask the question, what's the time to serve a batch of n customers as a function of n? I could give as a result this curve, but if I want to be a bit more synthetic, I will want to provide, not surprisingly, confidence intervals. So instead of giving this complete thing, I want to give one number and the accuracy of this number. This is what I did here. I computed the confidence interval for the mean and the confidence interval for the mean, and the confidence interval for the median. This is in red and in blue. The black we can ignore for the time being. So first thing to observe is how I summarize my data. In most cases is up to you. Sometimes there are cases if you're working, for example, in computational biology, you're just reproducing something in an environment where the metric is extremely well defined, so you have no choice. You have to give with a certain format. But most of the time for us, it's not the case. Most of the time, we are interested in things like, can you plot as a function of n the time it serves the time it takes to serve n customers. So you have the choice to use the mean or the median. Right? There is no, as we saw at last lecture, there is no fundamental reason to choose one or the other, except that the median is more convenient if we have no other constraints. So this is what I did here. I computed the confidence intervals for the median. And if I did it for many points, I would have a curve with an uncertainty bars, a cloud of uncertainty around it. And we see here the uncertainty is very small, which means that my number of simulation run was large enough. So this is applying the principle that we have in physics. In physics, we measure a physical phenomenon. We measure temperature, pressure, volume, speed, etc. Each of those things are measured with instruments that have some uncertainty because there is always physical instruments that they are never perfect. So we want to quantify the uncertainty of what we measure. Here it's exactly the same. So what you've learned in your physics undergrad course, you should continue to remember. We have to quantify the uncertainty with what we've done. The difference with physics experiments is here we have more leverage to modify the uncertainty. If our confidence interval would be huge, perhaps I could modify my simulation program, modify something in my simulation to get them smaller. Like, for example, the number of independent replications that I have. By the way, I did not mention how I computed these confidence intervals. What do you think we need to be careful in order to compute those different confidence intervals? I close the poll in a few seconds. And then there's a large diversity. Well, certainly we want the simulation runs to be independent, because all formulas we saw are for independent simulations. It would be nice if they are normally distributed as well, because then everything is simple. But in practice, this is asking for too much. I simulate a queuing system, I simulate my server, I simulate a wireless channel, or I simulate the output of an artificial intelligence estimating system. I don't have much control. I cannot really make sure that what I'm measuring will be normally distributed. So sometimes you may work on it by rescaling like we've seen, but sometimes this is asking too much. So most reasonable things are to make sure that they are independent. And, well, if they are not normally distributed and we want confidence interval for the mean, we will need to make sure that the number of replications that we have is large enough. Voila, that's all we will see for today. Next week, we will see how do we make sure that we produce independent runs of a simulation. That will be the next topic. And for this, we will need to dive a bit more into the random number generators. That's all for the lecture for today. The lab goes on. I wish all of you I hope all of you are doing well, even though it's hard to work under the circumstances that we have now. We all hope that we're able to go back to campus in a not so distant future. We give you support in the form of the lab sessions where we stay on the Zoom session. We also, of course, try to reply to the Moodle forum. So as quickly as possible, don't hesitate to post questions on the Moodle forum. And if you want to talk to us, we're always available. So if you need to talk to us outside of the lab sessions, outside of the lecture, send a mail. If it's several of you, because it has to do with a topic that's not well explained or not well understood, you can post that on Moodle, and then we'll do an ad hoc little Zoom session. Otherwise, we're always available for a small discussion on Zoom at any time when we're available, and that's possible every day with a short delay if you send a message to us. Voila, take care, enjoy, and see you very soon.